Alright, so in this problem we have a box of mass 35 kilograms that's being pushed with a force of 75 newtons and an angle of 30 degrees below the positive x-axis. The box is displaced 10 meters in the positive x direction. What is the work done on the box due to the push? What is the work done due to the force due to gravity? What is the work done due to the force normal? And what is the net work done on the box? Alright, so in order to be able to calculate work, remember work is equal to force that is parallel to the displacement. So before we can do anything, we have to draw a free body diagram because we know that our displacement is in the x direction. So when we do force parallel, we need parallel to the x direction. Alright, so let's draw a free body diagram. We have a box being pushed. So we have a force due to gravity in the negative y direction because the box has mass. It's being pushed with a force of 75 newtons, but we have to be careful because it's 30 degrees below the positive x-axis. And in fact, I'm going to have to move this label to the other side so that I can draw it down here in the fourth quadrant. So this is our force applied. So this would be our positive x-axis, and there would be 30 degrees in here. Alright, and it's sitting on a surface, so we're going to have a force normal pushing up. And there's no mention of friction, so we're just going to ignore friction. Alright, so our displacement's in the x. So that means when we go to do part A, where we want the work done on the box due to the push, that means we need the component of the push that's in the x direction, because we're displacing in the x direction. Because remember, we either do work equals force net in the x, and we're doing individual forces at first, we'll do force net at the end, times delta x. Which means that if I draw in my force push in the x direction, that component is adjacent, which is why I used cosine up here. So we're going to take our 75 newtons times the cosine, and because we're calculating work now and not just force, we're going to multiply it by the 10 meters, which gave me 750 joules. Remember, the units for work and energy are going to be joules. Alright, so in part B, we're being asked, what is the work done due to the force due to gravity? And if we look down here in our free body diagram, the force due to gravity is in the negative y direction. None of it points in the x direction. So that means I would plug in 0 for the force due to gravity in the x direction. And this is not an inclined plane problem, which means that there's none of the force due to gravity acting in the x direction, and I would take that times 10 meters, and 0 times 10 is still 0. So there's no work being done due to the force due to gravity on the box. Our next part asks us, what is the work done due to the normal force? So if we look down here in our free body diagram, the force normal points in the positive y direction. None of it's pointing off in the x direction, so we plug in 0 for the force normal in the x direction, because all of it's in the y direction, and multiply that by 10, and 0 times 10 is still equal to 0. So no work is being done by the force normal. Alright, in our last part of this problem, we're asked what is the net work done on the box. Alright, so we need to do force net in the x direction. And if we go back down to our free body diagram, the only force acting in the x direction is the force push in the x. So I put in force push times the cosine of theta, because that's how we calculate the x component of the force push, multiplied by the displacement in the x. So I plug in the 75 times the cosine of 30 degrees times 10 meters, and that gives us 750 joules. So let's expand this a little bit further. What happens if there was a force due to friction? So there's a force due to friction acting in the negative x direction. So let's pretend that was part of the problem. Let's talk about how this changes. Now there are two forces acting in the x direction. So our force net would equal force due to friction, which would be negative, plus force push times the cosine of theta. So when we plugged in here, we have a negative force due to friction plus force push times the cosine of theta times the change in the x direction. So notice I'm using parentheses because you need to multiply both forces times the displacement, because work is force times displacement. not force plus force times displacement. So make sure you get your parentheses in there and distribute. So this is an example of how you can expand this if you have more than one force.